Most mornings, the universe feels reassuringly predictable. Your alarm clock rings at precisely the programmed time, following the steady tick of quartz crystal oscillations. When you drop your phone, gravity pulls it toward the floor with mathematical certainty. Flip a light switch, and electricity flows through copper wires exactly as engineers designed the circuit to behave. The world operates according to clear, logical rules where causes precede effects in an unbroken chain of consequences. This is the reality. We've built our civilization upon a foundation of reliable physical laws that govern everything from the rotation of planets to the flow of electrons in our smartphones. For centuries, this classical worldview has served us extraordinarily well. We've constructed skyscrapers that stand for decades, launched spacecraft to distant planets, and created global communication networks that connect billions of people instantaneously. The universe, it seemed, was fundamentally comprehensible and predictable, but every so often, if you know where to look, hairline cracks appear in this seemingly solid foundation. You might encounter reports of particles that somehow exist in multiple locations simultaneously, defying every intuition about how objects should behave in space. Perhaps you read about experiments where the final outcome appears to depend on decisions that haven't been made yet, as if the future is reaching backward through time to influence the past. Or you learn about measurements that don't simply reveal the properties of particles, but actually create those properties through the very act of observation. Your first instinct might be to dismiss these claims as theoretical abstractions, mathematical curiosities that exist only in the rarefied realm of equations and thought experiments. After all, the world around you continues to behave with comforting predictability. Your car starts when you turn the key, your computer boots up when you press the power button, and the sun rises each morning just as it has for billions of years. Surely these quantum oddities, if they exist at all, must be confined to some distant corner of reality that has no bearing on the solid, dependable world of everyday experience. Yet the deeper you investigate, the more unsettling the picture becomes. These aren't merely theoretical speculations or mathematical artifacts existing in ivory tower laboratories. They represent real experiments conducted by respected researchers at institutions around the world, repeated countless times with increasingly sophisticated equipment, and verified by independent teams using different methodologies. The results consistently match the predictions of quantum theory, no matter how counterintuitive or philosophically disturbing those predictions might be. More importantly, these experiments aren't just academic exercises pursued for their own sake. The same quantum principles that produce such bewildering results also power the technology that surrounds us every moment of our lives. The computer processor running in your device right now depends on quantum tunneling effects that allow electrons to pass through barriers they classically shouldn't be able to cross. The GPS satellites guiding your navigation rely on quantum corrections to atomic clocks, accounting for relativistic effects that exist only when quantum mechanics and Einstein's relativity intersect. Medical imaging devices like MRI scanners operate using quantum magnetic resonance principles that have no classical equivalent whatsoever. The laser in your optical drive, the LED lights illuminating your room, and the solar panels generating clean energy all function because of quantum phenomena that classical physics simply cannot explain. We live in a world built on quantum foundations, yet those same foundations seem to violate our most basic intuitions about how reality should work. It's as if we've constructed a magnificent cathedral on ground that occasionally shifts and warps in impossible ways, yet somehow the structure remains stable and functional. This creates a profound paradox that extends far beyond the laboratory. Quantum mechanics stands as one of the most successful and precisely tested scientific theories in human history. Its predictions have been confirmed to extraordinary levels of accuracy, sometimes matching experimental results to 15 decimal places or more. Every technological application we've attempted, from semiconductors to superconductors, has vindicated the mathematical formalism of quantum theory with stunning precision. Yet despite this unprecedented success, A deep mystery remains at the heart of quantum mechanics. While we can calculate what will happen in quantum systems with remarkable accuracy, we still don't really understand what those calculations mean. The equations tell us how to predict the outcomes of experiments with extraordinary precision, but they don't explain why those outcomes occur, or what's actually happening in the physical world to produce such strange results. It's as if we have a perfect map of an alien landscape, complete with every road, landmark, and topographical feature marked in exquisite detail. But we still don't understand the language spoken by the inhabitants or the customs that govern their daily lives. We can navigate the territory with perfect accuracy, but the deeper meaning remains tantalizingly out of reach. This gap between mathematical success and conceptual understanding has persisted for nearly a century since quantum mechanics was first formulated by pioneers like Max Planck, Niels Bohr, and Werner Heisenberg. Generation after generation of physicists has grappled with the same fundamental questions about what quantum theory is actually telling us about the nature of reality. Some have proposed that particles don't have definite properties until they're observed by conscious beings. Others suggest that every possible outcome of every quantum event actually occurs simultaneously, but in separate, parallel universes that branch off from our own. Still others argue that the entire framework of classical logic needs to be abandoned when dealing with quantum systems. The lack of consensus among experts isn't due to insufficient data, inadequate mathematical tools, or simple intellectual stubbornness. Instead, it reflects something much deeper and more unsettling. Quantum mechanics appears to be pointing toward aspects of reality that lie beyond our current conceptual frameworks and perhaps beyond human comprehension entirely. The theory works with extraordinary precision, but it describes a world that seems fundamentally alien to our everyday experience and classical intuitions about how things should behave. This is what makes quantum paradoxes so significant and so deeply disturbing to contemplate. They aren't simply puzzles to be solved through clever reasoning or technical difficulties to be overcome with better equipment. Instead, they represent genuine cracks in our understanding of reality itself, places where our most successful scientific theories begin to reveal their limitations and point towards something deeper, stranger, and more mysterious than we had previously dared to imagine. Each paradox serves as a signpost marking the boundaries of human knowledge and indicating directions where revolutionary discoveries might be waiting. They whisper of a universe far more subtle and interconnected than our classical minds can easily grasp, where the very act of observation plays a fundamental role in creating the reality we experience. The journey we're about to undertake together will take us through some of the most profound and philosophically challenging paradoxes that quantum mechanics has revealed. We'll explore experiments that seem to violate the flow of causality, observations that appear to create reality rather than simply revealing pre-existing facts, and phenomena that challenge our most basic assumptions about space, time, consciousness, and the nature of existence itself. These aren't abstract philosophical questions divorced from practical reality, but concrete experimental results that force us to confront the possibility that the universe operates according to principles far stranger and more wonderful than we ever dared to imagine. Welcome to the quantum realm, where reality itself becomes a question rather than an assumption. The first crack to widen before our eyes cuts straight through something we thought we understood completely: the simple act of looking. In our everyday world, observation feels harmless and transparent. You can check the weather without changing the sky, read a thermometer without warming the room, or measure the speed of a passing car without affecting its motion. The act of measurement reveals information that already existed, like opening a book to read words that were already written on the page. But at the quantum scale, this fundamental assumption crumbles entirely. Looking isn't passive, it's a form of participation that doesn't merely reveal what exists but helps decide what becomes real. This isn't poetic metaphor or philosophical speculation. It's a precise description of what happens in laboratories around the world every single day, creating what physicists call the measurement problem. To understand how deeply this challenges our conception of reality, consider the simplest quantum story we can tell: a single electron approaching a barrier with two narrow openings like doorways in a wall. In the classical world, the electron would behave like a tiny marble, passing through one doorway or the other, leaving a simple pattern of impacts on a detection screen beyond. But quantum mechanics tells a different story entirely. When you fire electrons one by one toward these two slits, refusing to peek at which opening each electron uses, something extraordinary emerges on the detection screen. Instead of two simple bands of impacts corresponding to the two openings, you see a complex pattern of bright and dark stripes, an interference pattern that can only be created by waves overlapping and cancelling each other out, like ripples spreading from two stones dropped simultaneously into a still pond. The inescapable conclusion is that each individual electron somehow travels through both slits simultaneously, interfering with itself to create this wave-like pattern. The electron exists in what physicists call superposition, a genuine state of being in multiple conditions at once, not merely our ignorance about which condition it's actually in. Before any measurement occurs, the electron isn't definitively traveling through the left slit or the right slit. It's traveling through both, existing as a cloud of possibilities rather than a particle with a definite path. Now comes the truly unsettling part. Place a detector at one of the slits, a device sensitive enough to register which opening each electron passes through without significantly disturbing its motion. The moment you introduce this ability to gain which path information, the interference pattern vanishes completely. The wave-like behavior disappears, and the electrons begin acting like classical particles, each taking a definite path through one slit or the other. Two simple bands of impacts appear on the screen, exactly what you'd expect from tiny marbles. The same electrons, the same apparatus, the same distance between slits and screen. The only difference is whether you ask the question, which path did it take? Somehow, the mere potential to gain this information, even if no conscious observer ever looks at the detector's readings, is sufficient to collapse the electron's wave-like superposition into particle-like definiteness. The universe appears to know when information about the electron's path becomes available in principle, regardless of whether anyone actually accesses that information. This phenomenon reveals the heart of the measurement problem. Quantum mechanics describes particles before measurement using a mathematical entity called the wave function, a precise representation of all possible states the particle might be found in. Complete with the probability amplitudes for each possibility, the Schrödinger equation governs how this wave function evolves over time, changing smoothly and predictably according to deterministic mathematical rules. But the moment a measurement occurs, something dramatic and mysterious happens. The wave function, which had been spread across multiple possible outcomes, suddenly collapses into a single, definite result. The electron appears at one specific location, spinning in one particular direction, having traveled through one definite slit. All the other possibilities that existed moments before simply vanish, not gradually or partially, but instantaneously and completely. Here's what makes this so philosophically disturbing. Nothing in the mathematical formalism of quantum mechanics explains why or how this collapse occurs. The equations that describe quantum evolution are completely reversible and deterministic, containing no mechanism for the sudden, irreversible transition from possibility to actuality that characterizes every measurement. The theory works perfectly for calculating the probabilities of different outcomes, but it offers no explanation for the most crucial aspect of every quantum experiment, the moment when one specific outcome becomes real. Even more troubling, quantum mechanics provides no clear definition of what constitutes a measurement. Does it require interaction with a macroscopic detector? Must a conscious observer be involved? Will any interaction with the environment suffice? Can quantum systems measure each other? These questions have profound implications for our understanding of reality, yet the theory remains mysteriously silent on these fundamental details. The ambiguity runs deeper than mere technical precision. You can trace the measurement chain backwards step by step. The particle interacts with a detector. The detector's response triggers an electronic circuit. The circuit activates a computer. The computer displays a result on a screen. Light from the screen reaches a human eye. Neural signals fire in a brain, and nowhere in this sequence does the mathematics mark a privileged moment where collapse occurs. Quantum theory treats the entire chain, in principle, as one large entangled system evolving smoothly according to the Schrödinger equation. Yet we only ever experience definite outcomes, never the superpositions that the mathematics describes. The giants who first grappled with these quantum mysteries were deeply troubled by this paradox. Richard Feynman, renowned for making complex physics accessible, famously declared, "Nobody understands quantum mechanics," a candid acknowledgement of the theory's elusive core. Niels Bohr, one of quantum mechanics' founding architects, went further. Those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. Roger Penrose, with characteristic bluntness, has stated that quantum mechanics makes absolutely no sense. Perhaps most tellingly, Albert Einstein, whose work helped birth quantum theory, was profoundly unsettled by its implications, warning that if it is correct, it signifies the end of physics as a science. Even Erwin Schrödinger, whose equation describes quantum evolution, lamented, "I do not like it,
and I am sorry I ever had
anything to do with it." These voices across generations
remind us that the measurement problem isn't
a minor technical difficulty or a gap in our experimental capabilities. It's a fundamental challenge to our understanding of what it means for something to be real. Physicists have proposed numerous interpretations to resolve this paradox, each trading one set of conceptual difficulties for another. The Copenhagen interpretation, championed by Bohr, suggests that quantum systems simply don't possess definite properties until observed, making measurement the creative act that brings reality into being. But it leaves the crucial definition of measurement frustratingly vague. The many worlds interpretation takes a radically different approach, proposing that the wave function never collapses at all. Instead, every possible outcome of every quantum measurement actually occurs, each in its own parallel branch of reality. When you measure an electron spin, the universe splits, one branch where you observe spin up, another where you observe spin down. You experience only one branch, but both are equally real. This elegant mathematical solution avoids collapse entirely, but requires accepting an infinity of parallel universes branching with every quantum event. Decoherence theory focuses on how quantum systems interact with their environment, arguing that these interactions effectively constitute continuous measurement. Stray air molecules, thermal vibrations, and electromagnetic radiation constantly interact with quantum systems, entangling them with the larger world and destroying the delicate coherences that produce quantum weirdness. This explains why macroscopic objects behave classically. They're constantly being measured by their environment. However, decoherence explains why we stop seeing interference patterns, not why we experience one specific outcome rather than a statistical mixture of possibilities. Other approaches include objective collapse theories, which propose that wave function collapse is a real physical process that occurs spontaneously when systems reach certain thresholds of size or complexity. These models place the collapse mechanism within nature itself rather than in the act of observation, making testable predictions about when and how collapse occurs. Perhaps most controversially, some interpretations suggest that consciousness plays a fundamental role in collapsing wave functions. According to this view, the universe remains in quantum superposition until observed by a conscious mind, making awareness itself a physical force that shapes reality. While intriguing, This interpretation often draws criticism for being too philosophical and difficult to test experimentally. Regardless of which interpretation you favor, the central mystery persists. We possess a theory that describes the evolution of quantum systems with unprecedented accuracy, yet remains silent about the transition from possibility to concrete reality. It tells us what we will observe statistically, but not why we observe one specific outcome rather than another. This isn't merely about particles and probabilities, it challenges our most basic assumptions about the nature of existence itself. In classical physics, the observer stands apart from the observed, passively gathering information about a pre-existing world. You can study distant galaxies or analyze chemical reactions without fundamentally altering what you're investigating. But quantum mechanics suggests that the boundary between observer and observed becomes meaningless at the deepest level of reality. The measurement problem forces us to confront an uncomfortable possibility. Perhaps the act of observation isn't neutral discovery but active participation in creating the reality we experience. The questions we choose to ask don't simply reveal pre-existing answers, they help determine which answers become possible. In the double-slit experiment, asking which path creates a context where paths are exclusive and interference cannot occur. Asking what pattern appears creates a context where paths are complementary and interference flourishes. This realization opens the door to even more unsettling possibilities. If the choice of what to measure can influence the outcome, what happens when you delay that choice until after the quantum system has already interacted with detectors and left traces throughout the apparatus? Can a decision made in the present somehow reach backward to influence what happened in the past? The mathematics of quantum mechanics suggests this might be possible, leading us toward experiments that challenge not just our understanding of measurement, but our most fundamental assumptions about the flow of time itself. The measurement trap runs deeper than we initially imagined, ensnaring not just particles in superposition, but our entire framework for understanding causality, reality, and the role of consciousness in the physical universe. As we'll discover, some experiments suggest that even the temporal order of events might be subject to the strange rules that govern quantum measurement, forcing us to question whether the past is as fixed and immutable as our everyday experience. Ali suggests the measurement trap we've just explored becomes even more bewildering when we consider what happens if you delay the crucial decision until after the quantum event has already unfolded. This leads us into territory that challenges not just our understanding of observation, but our most basic assumptions about the flow of time itself. If the act of asking a question can change what becomes real, then what happens when you ask that question after the answer should already be written in stone? Imagine expanding our double-slit experiment in a way that seems impossible at first glance. You fire a single photon toward the familiar barrier with two openings, but instead of immediately deciding whether to monitor which path it takes, you allow the photon to complete its entire journey. It passes through the slits, traverses the empty space beyond, and registers its arrival at a detection screen. Only after this entire sequence is complete, after the photon has seemingly decided whether to behave like a wave or particle, after it has already left its permanent mark on the detector, only then do you make your choice about whether to gain information about which path it traveled. In any sensible universe, this delayed decision should be meaningless. The photon's behavior was locked in the moment it encountered the slits, long before you decided what kind of measurement to perform. Whether it traveled through both openings simultaneously as a wave or chose a definite path as a particle should have been determined by the time it reached the screen. Your later choice might affect future experiments, but surely it cannot reach backward through time to influence events that have already crystallized into history. Yet quantum mechanics predicts something extraordinary, and experiments have confirmed this prediction with unsettling precision. Your future choice about whether to erase or preserve path information will retroactively determine whether the photon exhibited wave-like or particle-like behavior during its earlier passage through the apparatus. This isn't a subtle statistical effect buried in complex analysis. It's a fundamental difference in the nature of what occurred, as dramatic as the difference between a ripple spreading across a pond
and a marble rolling down a
specific groove. The experimental setup that demonstrates this temporal paradox is called the delayed choice quantum eraser, and it represents one of the most philosophically challenging demonstrations in all of physics. The apparatus begins with a source that creates pairs of entangled photons, particles that share a mysterious quantum connection regardless of the distance separating them. Think of them as quantum twins, forever linked by an invisible thread that Einstein famously called spooky action at a distance. One photon from each pair, called the signal photon, travels toward our familiar double-slit arrangement. The other photon, called the idler photon, takes a completely different path toward a separate detection system. Here's the crucial insight that makes the temporal paradox possible. Measuring the idler photon can provide information about which slit the signal photon passed through, even though the two particles travel along entirely separate routes and never interact again after their birth. This quantum correlation allows you to gain which path information about the signal photon indirectly by examining its entangled partner rather than disturbing the signal photon itself. The temporal impossibility emerges when you arrange the apparatus so that the signal photon completes its entire journey passing through the slits, traveling across space and striking the detection screen before you decide what kind of measurement to perform on its entangled partner. The signal photon's fate appears sealed by the time it registers on the detector.
Yet your subsequent choice about how to measure
The idler photon will retroactively determine whether the signal photon behaved as a wave or particle during its earlier journey. If you choose to measure the idler photon in a way that reveals which path information about its entangled partner, you'll discover that the signal photons have behaved like particles throughout the experiment, each taking a definite path through one slit or the other. No interference pattern appears on the detection screen, just two simple bands of impacts corresponding to the two openings. But if you choose to perform a measurement on the idler photon that erases any possibility of gaining which path information, perhaps by scrambling the path data beyond any hope of recovery, then the signal photons will have behaved like waves throughout their journey, creating the characteristic zebra stripe interference pattern that can only result from traveling through both slits simultaneously. The temporal sequence defies comprehension. It's as if you threw a basketball through a hoop, watched it swish cleanly through the net, and then later decided whether you had been watching the throw. Somehow, that retroactive decision changes whether the ball actually went through as a single object or as a ghostly wave of possibilities that passed through multiple locations at once. The past appears to be written by the future, violating our most fundamental intuitions about causality and the immutable nature of historical events. Experimental teams have verified this prediction with increasingly sophisticated apparatus, extending the delay times between signal detection and idler measurement, eliminating potential loopholes and testing the effect with various types of particles. Every test confirms the same unsettling result. The choice of measurement strategy, even when delayed until after the quantum event has apparently concluded, determines the nature of what occurred in the past. This phenomenon forces us to confront profound questions about the nature of time itself. Perhaps our intuitive picture of time as a flowing river where past events recede into fixed history while future possibilities crystallize into present reality is simply wrong at the deepest level. Maybe time is more like a vast landscape where past, present, and future exist simultaneously, and our experience of temporal flow is merely how consciousness samples this eternal structure. The universe, careful as ever, refuses to let this become a time machine for sending messages to yesterday. You cannot use this setup to warn your past self about impending disasters or provide tomorrow's lottery numbers to your earlier incarnation. The interference pattern only emerges when you perform what physicists call coincidence counting, matching each signal photon to its corresponding idler measurement and sorting the results accordingly. The full, unsorted detection screen shows no interference at all, just a diffuse scatter of impacts that reveals nothing about the underlying wave-particle duality. Yet something profound is being revealed about the nature of reality itself. What changes isn't the physical surface of the detection screen, but the story you can honestly tell about how those impacts came to be. With which path information available, even in principle, the only consistent narrative is particle-like behavior. With that information erased beyond recovery, the consistent narrative becomes wave-like. The reality of the photon's path isn't a simple, standalone fact existing independently of observation. It's a property of the entire experimental context, including choices made after the event has seemingly concluded. Different interpretations of quantum mechanics translate this temporal puzzle into different metaphors. Some suggest that future boundary conditions help shape the past, making time a two-way street at the microscopic level. Others propose that no collapse ever happens. Both wave-like and particle-like histories unfold in parallel dimensions, and your delayed choice simply selects which branches correlations you uncover. Still others insist that physics should only predict the outcomes of complete experiments, not attempt to describe what happens between initial setup and final measurement. The delayed choice quantum eraser teaches us that measurement isn't a single moment when reality snaps to attention, but rather a web of constraints. What can in principle be known, what remains fundamentally indistinguishable, how distant events become correlated, that together determine which patterns can emerge from the quantum fog. Information isn't just something we extract from the world, it's part of the world's architecture, shaping which histories can be consistently told about what we observe. This realization opens the door to even more unsettling possibilities. If the availability of information can change which story about the past becomes coherent, what happens when different observers have access to different information about the same quantum event? Can two people witness identical circumstances yet reach fundamentally contradictory conclusions about what actually occurred? Not because someone made an error, but because reality itself fragments along the lines of who is doing the observing? The mathematics of quantum mechanics suggests this scenario isn't just possible, it might be inevitable, forcing us to question whether objective reality exists at all, or whether each conscious observer inhabits their own private version of the universe, sealed off from all others by the fundamental structure of quantum measurement itself. The unsettling possibility that different observers might experience fundamentally different versions of reality emerges naturally from the temporal paradoxes we've just explored. If the availability of information can retroactively determine which story about a photon's past becomes coherent, then what happens when two observers have access to different information about the very same quantum event? Do they inhabit separate, equally valid realities that can never be reconciled? This question leads us to one of the most philosophically disturbing paradoxes in quantum mechanics, first contemplated by physicist Eugene Wigner in 1961. Picture a laboratory sealed from the outside world, containing a quantum system prepared in superposition, perhaps a particle spinning simultaneously clockwise and counterclockwise. Inside this laboratory sits Wigner's friend, a skilled physicist equipped with precise measurement apparatus. The experimental procedure appears straightforward from the friend's perspective. Interact with the quantum system, read the detector output, and record a definite result. When the measurement concludes, let's say the outcome is spin up. The friend writes this result in a logbook, confident that the quantum superposition has collapsed into concrete reality. But now consider the situation from Wigner's perspective as he stands outside the sealed laboratory. He has not yet opened the door or learned what his friend observed. From this external vantage point, the entire laboratory, including the friend, the measuring apparatus, and the quantum particle remains part of one large, uncollapsed quantum system. According to the mathematical formalism of quantum mechanics, this entire system should exist in superposition until Wigner himself makes an observation. Here lies the heart of the paradox. The friend, from their internal perspective, has witnessed definite collapse and recorded a specific measurement outcome. Reality has crystallized into a single, unambiguous result. But Wigner, from his external perspective, sees the entire laboratory as a quantum system that hasn't collapsed, existing in superposition of all possible measurement outcomes. The particle isn't simply spin up or spin down, it's both. More disturbingly, the friend isn't simply someone who observed spin up or observed spin down. The friend exists in a superposition of having observed both outcomes simultaneously. Both perspectives follow logically from quantum mechanics principles, yet they paint completely contradictory pictures of reality. This isn't a question about incomplete information or subjective interpretation. It's a fundamental disagreement about the objective nature of physical events. Has the quantum system collapsed into a definite state, as the friend's direct observation suggests? Or does it remain in superposition until Wigner opens the laboratory door, as the mathematical formalism implies? For decades, this remained an intriguing thought experiment that physicists could debate in comfortable abstraction. The scenarios seemed to require putting conscious observers into quantum superposition, which appeared impossible with any foreseeable technology. But recent advances in quantum control have allowed researchers to create simplified versions of Wigner's friend scenarios using quantum systems as proxies for conscious observers.
And the results are deeply unsettling. In 2019,
a team of researchers published experimental results that demonstrated this paradox using photons and quantum detectors. They created situations where one quantum system could observe another, recording information about its state, while a third system observed the entire measurement process from outside. The results confirmed the theoretical prediction. Different observers could record genuinely contradictory facts about the same physical events, each correct within their own reference frame. These aren't mere differences of opinion or errors in data collection. The experiments reveal that quantum mechanics allows multiple, incompatible versions of reality to coexist simultaneously. One observer measures a definite outcome and records it as objective fact. Another observer, examining the same system from a different perspective, finds that no such collapse has occurred and the system remains in superposition. Both observers follow quantum mechanics correctly, yet reach fundamentally incompatible conclusions about what actually happened. This discovery pushes us far beyond familiar quantum strangeness like superposition or entanglement. Those phenomena, however counterintuitive, still preserve the notion that some underlying objective reality exists that all observers would agree upon with complete information. But Wigner's friend scenarios suggest this assumption, the foundation of scientific objectivity, might be fundamentally wrong. Reality itself might be observer-dependent, fragmenting along the lines of who is measuring and when. Consider the implications for scientific truth. In classical physics, when two scientists disagree about experimental results, we assume at least one has made an error, experienced equipment malfunction, or failed to account for relevant variables. There's an underlying objective reality serving as the final arbiter of truth. But if Wigner's friend scenarios reflect genuine features of the quantum world, then two equally competent scientists, using identical equipment and following proper procedures, might reach contradictory conclusions about the same experiment, and both could be correct within their respective frames of reference. The many worlds interpretation attempts to resolve this paradox by suggesting both observers are indeed correct, but they exist in different branches of reality. When the friend measures the particle's spin, the universe splits into multiple branches, one where the friend observes spin up, another where they observe spin down. Wigner, still outside the laboratory, hasn't yet split into these branches, so from his perspective, both outcomes remain in superposition. When he finally opens the laboratory door, he too branches with different versions of himself, entering different versions of the laboratory to meet different versions of his friend. Other interpretations take different approaches. Some suggest consciousness plays a special role in collapsing quantum systems, making the friend's conscious observation fundamentally different from mere physical interaction. Others propose that quantum mechanics simply doesn't apply to macroscopic systems like human observers, even in principle. Still others embrace the radical possibility that there is no resolution, that the paradox reflects a genuine feature of reality at its deepest level. Perhaps the universe doesn't possess a single, objective structure that all observers must agree upon. Instead, reality might be fundamentally perspectival, with each observer inhabiting their own version of the universe, created through their unique history of quantum interactions and measurements. This possibility challenges not just our understanding of physics, but our most basic assumptions about knowledge, truth, and shared reality. If different observers can experience genuinely different versions of the same events, what does it mean to speak of objective facts? How can science claim to discover universal truths if the universe itself fragments along the lines of observation? Can we ever truly communicate about reality if each of us inhabits a private quantum branch sealed off from all others? The Wigner's friend paradox forces us to confront the possibility that classical notions of single, shared reality might be illusions born from our macroscopic perspective. At the quantum level, where fundamental physics operates, reality might be far more fluid, personal, and strange than we ever dared imagine. Each conscious observer might be creating their own version of the universe through the very act of observation, weaving a unique narrative of existence that can never be fully reconciled with anyone else's story. This realization opens yet another door to even deeper mysteries. If observation can create multiple, incompatible realities, and if the timing of observation can influence what happened in the past, then perhaps our entire framework of cause and effect needs fundamental revision. Maybe the future doesn't simply emerge from the past through deterministic events. Maybe causality itself flows both ways, with future events reaching backward through time to help shape the past, creating a universe where effects can precede their causes, and tomorrow's decisions help determine
Yesterday's reality, the fragmenting of reality.
We've just witnessed pushes us toward an even more fundamental question about the nature of existence itself. If different observers can experience genuinely contradictory versions of the same events, and if future measurements can retroactively determine past behavior, then perhaps our most basic assumption about temporal flow, that causes always precede effects in an unbroken chain from past to future, represents nothing more than a macroscopic illusion concealing a far stranger underlying reality. Consider what happens when you examine the mathematical foundation of quantum mechanics itself. The Schrödinger equation, which governs how quantum systems evolve through time, possesses a remarkable and rarely contemplated property. It exhibits perfect time symmetry. Run the equation forward through time, and it describes quantum evolution with extraordinary precision. Run the same equation backward through time, and it works equally well, describing the reverse sequence with identical mathematical validity. At the deepest level of physical law, there exists no preferred direction for temporal flow. This mathematical symmetry might seem like an abstract curiosity, with no bearing on the tangible world around us. After all, our everyday experience screams that time has an absolute direction. We age but never grow younger, coffee cools but never spontaneously heats up, and memories point toward the past, while expectations face the future. The arrow of time feels as fundamental and unidirectional as gravity's pull toward Earth. Yet the quantum experiments we've explored suggest this intuitive picture might be profoundly incomplete. The delayed choice quantum eraser demonstrated that decisions made in the present can determine what happened in the past. Wigner's friend scenarios revealed that the timing of observation can influence which version of reality crystallizes from quantum possibilities. These aren't theoretical abstractions but experimental realities that force us to consider whether causality itself might flow in both directions at the quantum level. This possibility leads us into the strange territory of retrocausality, the idea that future events can influence past states through the fundamental structure of quantum mechanics itself. Unlike the dramatic causality violations depicted in science fiction, quantum retrocausality doesn't allow you to send messages to your younger self or prevent paradoxes through temporal manipulation. Instead, it suggests something far more subtle, that the complete description of any quantum event requires boundary conditions from both the past and the
Future. Imagine trying to understand
a river by examining only its mountain source while
ignoring its oceanic destination.
the river's present behavior, its meandering curves, depth, and current speed depends not just on where water originated but also on where it's flowing. Similarly, retrocausal interpretations suggest that a particle's present state emerges from constraints flowing both forward from its past and backward from its future, creating a universe where temporal influence moves in both directions simultaneously. This perspective finds concrete expression in advanced theoretical frameworks like the two-state vector formalism, developed by physicists Yakir Aharonov and Lev Weidman. This approach describes quantum systems using not one but two wave functions, one evolving forward from initial conditions, carrying information about how the system began, and another evolving backward from final measurements, carrying information about how the system will end. The particle's behavior at any moment emerges from the intersection of these dual temporal influences, like a valley carved by streams flowing from opposite directions. Under this interpretation, the puzzling results of delayed choice experiments become less mysterious. The photon doesn't mysteriously know about future measurement choices through some impossible temporal telepathy. Instead, its behavior throughout the entire experimental sequence reflects boundary conditions from both temporal directions, initial preparation and final detection, working together to determine which history becomes real. The photon's path through the double slits gets shaped simultaneously by how it was created and how it will ultimately be measured, making past and future equal partners in creating present reality. This retrocausal framework offers elegant solutions to several quantum paradoxes. The measurement problem, why quantum superpositions collapse into definite outcomes, might reflect the intersection of forward-evolving possibilities with backward-evolving constraints from future observations. The apparent instantaneous correlation between entangled particles separated by vast distances might not require faster-than-light communication if both particles are simultaneously influenced by future measurements that haven't occurred yet from our limited temporal perspective. Yet, embracing retrocausality opens profound philosophical chasms about the nature of free will and temporal experience. If your future choices help determine past events, are those choices truly free, or are they constrained by consistency requirements with events that have already unfolded? Perhaps our entire experience of making decisions in the present that influence the future represents a cognitive illusion created by consciousness moving through a fixed four-dimensional structure where past, present, and future coexist eternally. This leads naturally to the concept of the block universe, where time doesn't flow like a river but exists as a complete, unchanging landscape. Your birth, your current reading of these words, and your eventual death all exist simultaneously as different locations in this temporal geography. What you experience as the passage of time might simply reflect consciousness sampling different cross-sections of this eternal structure, like a spotlight moving across a vast painting, illuminating different regions in sequence but never changing the painting itself. Some physicists find this block universe perspective liberating, resolving temporal paradoxes by eliminating the flow of time entirely. Others find it deeply disturbing, reducing human experience to predetermined patterns frozen within spacetime's crystalline structure. If the block universe reflects reality, then every decision you'll ever make already exists as part of the eternal framework. Your sense of choosing between alternatives might be an illusion created by consciousness encountering pre-existing temporal patterns. Experimental tests of retrocausality remain challenging but not impossible. Researchers have designed sophisticated experiments that could distinguish between retrocausal and conventional interpretations of quantum mechanics, searching for subtle signatures of future influence embedded within present measurements. Some studies claim preliminary evidence for retrocausal effects, though the results remain controversial and require extensive verification. The implications stretch far beyond laboratory physics into the deepest questions about reality's architecture. If retrocausality reflects genuine features of the universe, then existence operates more like a vast, interconnected web where every event influences every other event across both space and time, rather than a mechanical clockwork where causes precede effects in orderly sequence. Past, present, and future become different perspectives on a single, timeless reality where influence flows in all temporal directions simultaneously. This possibility transforms our understanding of consciousness itself. We might not be biological machines processing information from past to future, but rather aware patterns embedded within space-time's eternal structure, experiencing temporal flow as we trace our predetermined paths through the block universe. Our decisions, memories, and experiences might all exist simultaneously as different aspects of our four-dimensional selves, distributed across time like sculptures distributed across space. The universe revealed by quantum mechanics operates according to principles far stranger than our classical intuitions suggest. Time might be bidirectional at fundamental levels, reality might fragment along lines of observation, and the future might help write the past through subtle boundary conditions that respect causality while transcending our naive understanding of temporal sequence. Yet even as retrocausality challenges our temporal assumptions, it opens the door to an even more mysterious possibility. If future events can influence past states, and if different observers can experience contradictory realities, then perhaps the quantum correlations that connect distant particles also enable forms of coordination that transcend both space and individual consciousness. In carefully controlled situations, separated observers might achieve perfect synchronization without exchanging any signals whatsoever, as if the universe itself were facilitating a form of silent communication that operates beyond the ordinary limits of cause, effect, and the speed of light. The bidirectional flow of quantum influence we've just encountered naturally raises an even more fundamental question about the nature of space itself. If future events can reach backward through time to help shape the past, then perhaps the boundaries we draw between distant locations in space are equally illusory. What we're about to explore challenges not just our understanding of time, but our most basic assumptions about separation, independence, and the very meaning of distant in a quantum universe. Consider a coordination challenge that seems to violate every principle of information theory and communication. Imagine yourself and a friend separated by vast distances. Perhaps you're stationed in New York while they're positioned in Tokyo with absolutely no means of communication between you. You're each sealed in isolation chambers with no windows, phones, internet connections, or any conceivable method for exchanging information. The walls are impenetrable to all known forms of radiation, and you're monitored to ensure no signals can pass between your locations. Now a referee presents you both with an apparently simple game. Each of you will be asked a question chosen randomly from a predetermined list, and you must respond with either yes or no. The challenge lies in coordinating your responses according to specific rules that require your
answers to correlate in precise patterns depending on which
questions are asked. Success demands perfect synchronization across thousands of rounds. with even a single coordination failure resulting in complete defeat. In any classical universe, your best strategy would involve extensive preparation, perhaps developing a comprehensive lookup table specifying exactly how to answer every possible combination of questions. You might devise intricate decision trees, memorize complex algorithms, or establish elaborate coding systems. With sufficient planning, you could significantly improve your chances of success, achieving perhaps 75 or even 80% coordination across many rounds. But here's where classical physics hits an insurmountable wall. No matter how brilliant your strategy, how extensive your preparation, or how perfectly you execute your plan, certain combinations of questions will inevitably force you into impossible coordination requirements. The mathematics of classical probability theory establishes absolute limits on achievable correlation without communication. Perfect synchronization remains forever beyond reach, not because of inadequate planning or execution errors, but because the universe itself forbids such coordination through purely classical means. Now introduce a quantum twist that transforms the impossible into the inevitable. Suppose that before your separation, you and your friend each take possession of one member of a pair of quantum particles prepared in an entangled state. These particles share a connection that transcends ordinary notions of space and distance, a bond so fundamental that measuring one particle instantly determines properties of its partner, regardless of the cosmic distances separating them. This isn't communication in any conventional sense, but rather the manifestation of a deeper unity where the two particles remain aspects of a single,
indivisible quantum system. When the coordination game begins,
you base your answers not on any prearranged classical strategy, but on quantum measurements performed on your local particle. Your friend follows the same protocol with their entangled partner. Despite having no communication channel, no shared information during the game, and no method for coordinating your responses in real time, you achieve something that classical physics declares mathematically impossible: perfect synchronization across every single round. This phenomenon, known as quantum pseudo-telepathy, has been demonstrated repeatedly in laboratories worldwide using increasingly sophisticated experimental protocols. The effect is genuine, reproducible, and thoroughly verified, yet it shatters our fundamental assumptions about information, locality, and the nature of physical correlation. Two observers can coordinate their actions flawlessly without any form of communication whatsoever, achieving synchronization levels that classical theory proves impossible. Consider the famous magic square game, which illustrates this impossibility with mathematical precision. Two players must fill a 3x3 grid with entries of +1 or 1, following specific rules about how rows and columns must sum. Player Alice receives a randomly chosen row number and must
fill that entire row such that the product
of her 3 entries equals +1. Player Bob receives a
randomly chosen column number and must fill that
column, so the product of his 3 entries equals 1. They cannot communicate during the game, and the entry where Alice's row intersects Bob's column must match between their grids. Classical analysis reveals that no strategy can guarantee success in every round. The mathematical constraints create scenarios where perfect coordination becomes logically impossible. Yet players equipped with appropriately entangled quantum states and measurement protocols achieve flawless performance, winning every single game without exception. Their individual measurements appear random from each player's local perspective, yet somehow conspire to satisfy the game's requirements with supernatural precision. The GHZ game, named after physicists Greenberger, Horn, and Zeilinger, extends this impossibility to 3 players facing even more intricate coordination requirements. Again, classical strategies inevitably fail against certain question combinations, while quantum protocols enable perfect success rates that seem to mock the very foundations of probability theory and information science. These demonstrations reveal something profound about the architecture of reality itself. The quantum correlations enabling pseudo-telepathy don't emerge from faster-than-light communication or hidden information channels. Instead, they reflect the fundamental non-separability of entangled quantum systems. The particles don't exchange signals because they were never truly separate entities capable of independent existence. They remain components of a unified quantum whole that extends across arbitrary distances in space. This realization forces us to abandon classical assumptions about locality and realism, two pillars supporting our intuitive
understanding of physical reality.
Locality demands that objects can only influence their immediate surroundings, with all effects propagating at finite speeds limited by light. Realism insists that physical properties possess definite values even when unobserved, existing as objective features of reality independent of measurement. Quantum pseudo-telepathy demonstrates that at least one of these principles must be sacrificed. If the universe preserves locality, then particles cannot have predetermined properties that would enable classical coordination strategies. If realism holds and properties exist independently of observation, then locality must be violated through instantaneous correlations spanning cosmic distances. Decades of experimental tests, beginning with John Bell's revolutionary inequalities, have confirmed that quantum correlations exceed any limits compatible with both locality and realism simultaneously. Most physicists interpret these results as evidence against realism rather than locality. Quantum systems don't possess definite properties until measured, existing instead in superpositions of possibilities that collapse into specific outcomes only upon observation. Entangled particles don't communicate across space because they represent different aspects of a single quantum entity whose properties crystallize simultaneously when any component is measured, regardless of spatial separation. This perspective transforms our understanding of what it means for systems to be separate or connected. At the quantum level, apparent boundaries between distinct objects might reflect limitations of our macroscopic perception rather than genuine physical divisions. The entangled particles achieving perfect coordination aren't violating causality or exchanging forbidden signals. They're simply manifesting the unified nature of quantum reality that classical intuitions fail to recognize. The implications
Cascade through everything we've explored so far.
If observation can fragment reality into incompatible narratives, if future choices can influence past events, and if distant systems can coordinate perfectly without communication, then the universe operates according to principles far more subtle and interconnected than classical physics suggests. Properties don't belong to objects as permanent, intrinsic features, but emerge from the relational context of measurement and observation. This relational view of quantum properties opens the door to an even more startling possibility. If the connection between particles and their characteristics can be so flexible, if perfect coordination can occur without communication, if measurement contexts can determine which properties become real, then perhaps the bond between an object and its defining traits isn't as unbreakable as classical intuition demands. Could there be circumstances where a particle and one of its fundamental properties part ways, at least temporarily, appearing in different locations, like a grin separated from its cat? The mathematics of quantum mechanics suggest this impossible scenario might actually be possible through carefully designed experiments that probe the delicate boundary between what belongs to an object and what emerges from the context of observation itself. As we'll discover, the same quantum principles that enable silent coordination across vast distances also permit the separation of properties from their apparent owners, revealing that even the most basic assumptions about identity and possession require fundamental revision in the quantum
realm, the silent coordination we've just witnessed
between distant quantum systems naturally raises an even more fundamental question about the architecture of reality itself. If entangled particles can transcend classical boundaries of space to achieve perfect synchronization without communication, then perhaps the boundaries we draw between objects and their properties are equally illusory. What we're about to explore challenges our most basic assumption about identity, that things and their characteristics form inseparable wholes that travel together through space and time. Consider how naturally we assume that properties belong to
objects in our everyday world.
When you move a spinning coin from one table to another, its rotation accompanies the journey without question. The coin's position and its angular momentum travel together as unified aspects of a single entity. Similarly, when you carry a warm cup of coffee across a room, the heat moves with the liquid. You never expect the temperature to linger behind while the cup relocates elsewhere. Objects and their attributes form coherent unities that classical physics treats as fundamentally indivisible. But quantum mechanics, as we've repeatedly discovered, delights in shattering such classical expectations. The same mathematical framework that enables perfect coordination without communication also permits something that sounds like pure fantasy: the separation of a particle's properties from the particle itself. Under carefully controlled conditions, quantum systems can exhibit behavior where a particle travels along one path while one of its defining characteristics travels along a completely different route, like a grin detached from its cat. This impossible scenario emerges from experiments inspired by Lewis Carroll's Cheshire cat, that enigmatic feline who could vanish while leaving only his smile floating mysteriously in mid-air. The quantum version involves neutrons, electrically neutral particles that possess both definite position and an intrinsic quantum property called spin. Unlike classical rotation, quantum spin represents a fundamental characteristic as essential to the neutron's identity as mass or charge, determining how it interacts with magnetic fields and other particles. The experimental apparatus resembles the interferometers we've encountered throughout our quantum journey, devices that split a particle's path into multiple routes that later reconverge. A neutron beam enters the device and encounters a path splitter that creates quantum superposition. The neutron simultaneously travels along both possible routes, existing in multiple locations at once until measurement forces it to choose a definite path, the Cheshire cat effect emerges through a sophisticated manipulation involving weak measurements, gentle probes that extract information without completely destroying the delicate quantum superposition. Unlike strong measurements that force immediate collapse into definite states, weak measurements barely graze the quantum system, gathering only statistical hints while preserving the coherence necessary for quantum interference effects. Researchers carefully engineer the neutron's quantum state and measurement protocols so that when they perform these gentle probes, they discover something extraordinary. The neutron appears to travel predominantly along one arm of the interferometer, while its spin property appears to travel predominantly along the other arm. The particle and its defining characteristic have somehow become spatially separated within the apparatus. This separation isn't
A single dramatic event, but emerges from
statistical patterns collected across thousands of trials. Each individual weak measurement yields results that appear random and meaningless. But when researchers analyze the accumulated data, clear patterns emerge showing that the amplitude for detecting the neutron particle concentrates in one location, while the amplitude for detecting its spin concentrates elsewhere. The neutron's identity fractures across space, with different aspects appearing in different locations. The technique relies on careful pre-selection and post-selection protocols. Scientists first prepare the neutron in a precisely defined initial state, then allow it to traverse the interferometer while performing weak measurements along both arms. Finally, they accept only those experimental runs where the neutron is detected in a specific final state. This filtering process reveals correlations that would remain hidden in unselected data, unveiling the statistical signature of property separation. The mathematical description involves quantum amplitudes, complex numbers encoding probabilities that can exhibit counterintuitive behavior. Through careful engineering, researchers create situations where the amplitude for finding the neutron is large in one arm, while the amplitude for detecting its spin is large in another arm. The neutron becomes less like a tiny marble with spin attached and more like a cloud of quantum possibilities where different properties have different spatial distributions. This separation challenges our most fundamental concepts of identity and existence. In classical physics, a neutron represents an indivisible entity whose properties travel with it wherever it goes. But the quantum Cheshire cat effect suggests that particles might be more like collections of separable attributes that can drift apart under appropriate conditions. Properties don't belong to objects as permanent, intrinsic features, but emerge from the relational context of measurement and observation. Different interpretations of quantum mechanics offer various explanations for this mysterious phenomenon. Some suggest the effect reflects the fundamentally relational nature of quantum properties. Characteristics don't inhere in particles as fixed features, but arise from measurement contexts. When these contexts become sufficiently complex, different properties can respond to different aspects of the experimental setup, creating apparent spatial separation. Others propose that the Cheshire cat effect demonstrates the inadequacy of classical language for describing quantum phenomena. We use concepts like particle and spin borrowed from classical physics, but these might be fundamentally inappropriate for quantum systems. The apparent separation might reflect our attempt to force quantum behavior into conceptual frameworks that cannot accommodate the underlying reality. The many worlds interpretation suggests that neutron and spin don't actually separate within a single universe. Instead, different branches of reality emphasize different aspects of the neutron's identity, with measurement sampling across parallel realities to create the statistical appearance of property separation within our limited observational frame. Regardless of interpretation, the effect reveals something profound about quantum identity. The boundaries we draw around objects, the properties we assign to particles, and the relationships we assume between characteristics and their owners all become fluid and context-dependent in the quantum realm. Reality doesn't consist of well-defined objects with fixed properties, but rather patterns of possibility that crystallize into apparent definiteness only through measurement and observation. This realization connects deeply with all the quantum mysteries we've explored. If properties can separate from objects, then measurement becomes even more enigmatic. What exactly is being measured when the measured system lacks definite identity? If different observers can experience different realities, and if properties can exist independently of their apparent owners, then our entire framework of objective physical truth requires fundamental revision. The quantum Cheshire cat forces us to confront the possibility that classical concepts of identity, ownership, and existence might be emergent illusions created by consciousness interacting with quantum possibilities. At the deepest level of reality, there might be no things with properties at all, but rather patterns of correlation and relationship that create the appearance of objects and characteristics. Only when filtered through the limited perspective of classical observation, this dissolution of identity boundaries naturally leads us toward an even more disturbing possibility. If the properties of particles can separate from the particles themselves, and if consciousness plays a role in determining which quantum possibilities become real, then what happens when we apply these principles to consciousness itself? Could there be quantum scenarios where the very continuity of conscious experience becomes subject to the same strange rules, creating situations where awareness might follow some branches of possibility while abandoning others? The mathematics of quantum mechanics suggest such scenarios aren't merely theoretical curiosities, they might represent inevitable consequences of taking quantum theory seriously when applied to conscious observers navigating the branching pathways of quantum reality. The dissolution of identity boundaries we've just witnessed pushes us toward the most personally disturbing implication of quantum mechanics. What happens when these strange rules apply not just to particles and their properties, but to consciousness itself? If quantum systems can exist in superposition until measured, if properties can separate from their owners, And if reality fragments along lines of observation, then perhaps the continuity of conscious experience follows the same bizarre principles that govern neutrons drifting through interferometers. This realization leads us into territory that transcends abstract physics and enters the realm of existential philosophy through one of the most unsettling thought experiments in quantum mechanics, the quantum suicide scenario. This isn't a proposal for any real experiment. It's a purely theoretical exploration that reveals disturbing implications of taking quantum mechanics seriously when applied to conscious
Observers, the thought experiment emerges naturally
from the many worlds interpretation which we've encountered throughout our quantum journey. According to this framework, the wave function never actually collapses into a single outcome. Instead, every quantum event with multiple possible results causes reality itself to branch into parallel universes, each containing a different outcome. When a particle's spin is measured, the universe doesn't choose up or down, it splits into two branches, one where the measurement yields each result. Both outcomes occur, but in separate, non-communicating realities. This branching happens constantly throughout the universe. Every quantum interaction, radioactive decay, thermal fluctuations, neural processes in your brain triggers universal splitting according to many worlds theory. Reality resembles an infinitely expanding tree where each quantum moment spawns countless new branches, creating an ever-growing multiverse of parallel possibilities. Now consider your place within this branching structure. At this very moment, quantum processes in your brain are creating branches where slightly different versions of you continue reading with subtly altered thoughts and neural states. Most variations remain imperceptibly small, but the branching is real and continuous, distributing your identity across countless parallel realities. The quantum suicide thought experiment explores what happens when these principles encounter mortality itself. Imagine a device connected to a quantum random number generator, perhaps monitoring radioactive decay with exactly 50% probability of detecting a particle within any given interval. Connect this quantum trigger to a mechanism that activates only upon detection, creating a situation where survival depends entirely on quantum chance. From an external observer's perspective, the outcome appears straightforward. Across many trials, approximately half the participants would survive, while half would perish, following classical statistical predictions. But from the first-person perspective of the participant, many worlds suggest something far stranger. When the quantum trigger activates, reality branches into two paths, one where detection occurs and consciousness ends, another where no detection happens and awareness continues. The crucial insight is that conscious experience can only persist along branches where the observer remains alive to experience anything at all. This creates a selection effect unlike anything in classical physics. Your stream of consciousness doesn't randomly sample all possible branches. It necessarily follows only those paths where awareness can persist. From your subjective viewpoint, you find yourself repeatedly surviving against increasingly improbable odds, not through luck or intervention, but because consciousness cannot exist in branches where it has been extinguished. Extend this scenario across multiple trials, and the implications become deeply unsettling. Even if survival probability drops to 1 in a million or 1 in a billion, there will always exist some branches where you continue through sheer quantum chance. Your subjective experience follows these increasingly improbable paths, creating a form of quantum immortality where consciousness persists indefinitely by threading through narrow corridors of survival within the vast multiverse. This
doesn't mean you become invulnerable in the everyday
world that external observers share. From their perspective, you remain as mortal as anyone else. But from your internal perspective, your stream of awareness continues by always finding itself in branches where survival remains possible. No matter how unlikely those branches become, the scenario becomes even more disturbing when you consider what kinds of survival these rare branches might contain. Perhaps you're the sole survivor of catastrophic events that eliminate everyone else. Maybe you persist in states of severe injury or isolation that would normally prove fatal. The branches where consciousness continues might not represent pleasant outcomes, but merely the minimal conditions necessary for awareness to persist. This quantum immortality doesn't offer traditional comforts associated with eternal life. Instead, it suggests existence trapped within the most improbable corners of reality, experiencing increasingly bizarre and isolated circumstances as more probable branches lead to extinction. Your subjective timeline might stretch through scenarios that become progressively more surreal and lonely as the multiverse evolves. The thought experiment raises profound questions about identity across quantum branches. Are all these parallel versions really you in any meaningful sense? Or do they represent distinct conscious entities sharing memories up to branching points? If consciousness follows only surviving branches, what happens to awareness in branches where death occurs? This connects with broader questions about observer selection and what philosophers call the anthropic principle. Perhaps the very fact that you find yourself conscious and capable of contemplating these questions reflects a selection effect. You exist in a branch where conditions permit conscious observers to emerge and persist. Your ability to wonder about quantum mechanics might itself be evidence that you inhabit one of the rare branches where intelligence and scientific understanding can develop. The quantum suicide paradox transforms our understanding of existence from a single, precious timeline to a vast network of possibilities where consciousness navigates through quantum branches according to principles we barely comprehend. It suggests that personal survival might depend not on avoiding danger in classical terms, but on deeper questions about whether quantum mechanics permits conscious experience to persist across reality's branching structure. Yet even as this thought experiment challenges our understanding of consciousness and survival, it opens the door to an even more fundamental mystery about information and existence. If consciousness represents a pattern of information that can persist by following improbable branches through the quantum multiverse, what happens to information itself when it encounters the ultimate boundary, the event horizon of a black hole where not even light can escape? The mathematics suggest this scenario creates paradoxes about information conservation that challenge our understanding of both consciousness and physical law at the deepest possible level, forcing us to confront whether the universe can truly destroy information or whether it must be preserved in forms we don't yet comprehend. The preservation of consciousness across quantum branches that we've just explored
Naturally confronts us with the ultimate test of
information conservation itself. If awareness can persist by threading through improbable survival paths because quantum information cannot be destroyed, then what happens when information encounters the most extreme boundary the universe can create? A place where space and time themselves collapse into mathematical singularities, where not even light can escape, and where the very notion of outside loses all meaning. Black holes represent nature's most perfect information traps, regions where gravity has become so intense that it warps space-time into inescapable wells. When a massive star exhausts its nuclear fuel and collapses under its own gravitational pull, it can create these cosmic monsters that devour everything in their vicinity. The event horizon marks the point of no return. Cross this invisible boundary, and you become permanently severed from the rest of the universe, doomed to fall toward the central singularity where all known physics breaks down. From the perspective of external observers, anything that falls into a black hole simply vanishes from reality. The complex molecular structures of planets, the intricate neural patterns that might encode consciousness, the detailed quantum states of countless particles, all of this information appears to be erased completely. General relativity describes black holes using just three simple numbers: mass, electric charge, and angular momentum. Every other detail about what created the black hole or what has fallen into it since becomes irrelevant. lost beyond any possibility of recovery. This erasure creates a profound crisis because quantum mechanics operates according to a fundamental principle that makes information conservation
as absolute as energy conservation.
In quantum theory, information about a system's complete state cannot simply vanish. It must always be preserved somewhere, even if it becomes scrambled beyond practical recognition. This isn't merely an abstract mathematical requirement, but the foundation that makes quantum mechanics internally consistent. If information could be destroyed, then the probability relationships between quantum states would break down, making the entire theory mathematically incoherent. The principle of unitarity ensures that if you know the complete quantum state of a system at any moment, you can, in principle, determine its state at any other time, both past and future. This reversibility underlies every quantum calculation and prediction. Without it, you couldn't trace outcomes backward. Quantum probabilities wouldn't add up to certainty, and the entire predictive power of the theory would collapse. Information conservation isn't just a nice idea, it's the mathematical backbone that keeps quantum mechanics from falling apart. The conflict between these two successful theories seemed like an abstract philosophical problem until Stephen Hawking made a discovery in the 1970s that transformed it into a concrete physical paradox. Applying quantum mechanics to the extreme gravitational fields near black hole event horizons, Hawking found that these objects cannot remain perfectly black. The violent curvature of space-time creates pairs of virtual particles that briefly pop into existence before annihilating each other. Occasionally, one particle from such a pair falls into the black hole while its partner escapes, creating a steady stream of radiation that slowly drains the black hole's mass. This Hawking radiation means black.
Holes aren't eternal prisons, but slowly evaporating objects that will
eventually disappear completely, leaving behind only empty space and fading thermal radiation. Given enough time, vastly longer than the current age of the universe, for stellar mass black holes, even the largest black holes will radiate away their entire mass and vanish. Hawking's original calculations revealed something deeply disturbing about this radiation. It appears completely random and thermal, carrying no information about what fell into the black hole. The escaping photons seem to know nothing about whether the black hole formed from hydrogen, iron, or even conscious beings with complex neural patterns. If this analysis is correct, then when a black hole finally evaporates completely, all information about everything that ever fell into it would be permanently destroyed, violating quantum mechanics' most fundamental requirement. This creates the information paradox in its starkest form. Either general relativity is wrong about black holes being perfect information destroyers, or quantum mechanics is wrong about information conservation being absolute. Both theories work extraordinarily well in their respective domains and have passed every experimental test. Yet they make contradictory predictions about this crucial scenario. The paradox deepens when you consider quantum entanglement. Imagine you possess one member of an entangled particle pair while a friend holds the other. If your friend throws their particle into a black hole, quantum mechanics insists the entanglement between your particles must be preserved. But if your friend's particle is truly lost forever, then your particle becomes entangled with something that no longer exists in the observable universe, a situation that quantum theory cannot describe consistently. Physicists have proposed various solutions, each carrying profound implications for our understanding of reality. Some argue that information is indeed encoded in Hawking radiation, but in such a subtle, complex way that we haven't learned to decode it. Recent theoretical work suggests this might happen through what's called the Page curve. Early radiation appears thermal and ignorant, but after a critical point, correlations begin to emerge that allow information to flow out more efficiently until the black hole's complete evaporation. The holographic principle offers another revolutionary approach, suggesting that all information about a black hole's interior is actually stored on its two-dimensional surface. like a hologram encoding three-dimensional images on flat surfaces. As the black hole evaporates, this surface information gradually leaks out through Hawking radiation, preserving quantum information conservation while respecting the curved space-time geometry that general relativity describes. More radical proposals include the firewall hypothesis, which suggests the event horizon isn't the smooth boundary described by general relativity, but rather a violent region where infalling matter encounters a wall of high-energy particles. This would preserve information by preventing anything from actually entering the black hole's interior, but it would violate general relativity's prediction that crossing an event horizon should feel smooth and unremarkable. Recent developments focus on the deep connection between quantum entanglement and space-time geometry itself. Some researchers propose that black hole interiors might be connected to their exteriors through quantum wormholes, allowing information to escape through mechanisms that respect both general relativity and quantum mechanics. Others suggest that the very concept of a black hole interior might be an illusion created by our limited perspective, with all physics actually occurring on or near the event horizon. These solutions share a common theme. They force us to abandon classical intuitions about locality, about what counts as inside versus outside, and about whether reality must tell a single, consistent story to all observers. Information might be preserved, but only by accepting that space-time and quantum entanglement are two faces of the same underlying reality, and that different observers might experience fundamentally different versions of the same events. The black hole information paradox connects directly with every quantum mystery we've explored. If consciousness can persist by following improbable branches through the quantum multiverse, if different observers can experience contradictory realities, and if the future can influence the past, then perhaps the preservation of information in black holes follows similarly counterintuitive principles. The universe might conserve information not through mechanisms we can easily visualize, but through deep quantum correlations that transcend our classical understanding of space, time, and causality. This realization brings us full circle to the central mystery that underlies every paradox we've encountered. Whether we're discussing wave function collapse, delayed choice experiments, observer-dependent realities, or information preservation in black holes, we inevitably return to the same fundamental question: what transforms quantum possibilities into definite realities? Somewhere in the gap between mathematical formalism and concrete experience, between probability and actuality, lies the key to understanding not just black holes or quantum mechanics, but the very nature of existence itself. The act of measurement, observation, and conscious awareness seems to play a crucial role in determining what becomes real, but we still don't understand how or why this transformation occurs. The preservation of information across cosmic boundaries that we've just confronted brings us face to face with the deepest mystery underlying every quantum paradox we've encountered. Whether we're contemplating particles that exist in multiple states simultaneously, observers who experience contradictory realities, or information that somehow survives the ultimate cosmic erasure, we inevitably return to the same fundamental enigma. What transforms the ghostly realm of quantum possibilities into the concrete world of definite experience? This question cuts to the very heart of existence itself. Throughout our journey, we've seen how measurement acts as the mysterious boundary between the quantum and classical worlds. Yet we've never truly examined what measurement actually is or why it possesses such reality-shaping power. Every paradox we've explored ultimately traces back to this single, profound mystery that has haunted physics for nearly a century. Consider the pattern that emerges when we look back across our quantum landscape. The double-slit experiment revealed that asking which path fundamentally changes what occurs, transforming wave-like behavior into particle-like behavior. The delayed choice quantum eraser showed that this transformation can reach backward through time, with future decisions determining past behavior. Wigner's friend demonstrated that the timing and perspective of measurement can create incompatible realities for different observers. The quantum Cheshire cat effect revealed that even the relationship between objects and their properties becomes fluid under certain measurement conditions. Each of these phenomena points toward the same unsettling conclusion. Measurement isn't simply the passive revelation of pre-existing properties, but an active process that participates in creating the reality we experience. Yet quantum mechanics provides no explanation for how or why this creative act occurs. The mathematics describes the pre-measurement state with extraordinary precision through the wave function, a complex mathematical entity that encodes all possible measurement outcomes and their associated probabilities. The Schrödinger equation governs how this wave function evolves smoothly and deterministically through time, following rules as precise as clockwork. But nowhere in this mathematical framework does anything explain the sudden, discontinuous collapse from multiple possibilities into a single, definite result. This collapse isn't gradual or partial, it's instantaneous and complete. One moment an electron spins in all directions simultaneously. The next moment it possesses one definite orientation. The transition happens in zero time, violating the smooth, continuous evolution that characterizes every other aspect of quantum mechanics. It's as if the universe suddenly switches from operating according to quantum rules to operating according to classical rules, with no mechanism to explain this dramatic transformation. The mystery deepens when you attempt to identify exactly what constitutes measurement. Does a particle interacting with a detector count as measurement? What about the detector triggering an electronic circuit? The circuit activating a computer? The computer displaying results? Light reaching a human eye?
Neural signals firing in a brain?
The emergence of conscious awareness? Quantum mechanics offers no guidance for drawing this crucial boundary. According to the mathematical formalism, the entire chain from particle to consciousness forms one large quantum system evolving according to the Schrödinger equation. The detector becomes entangled with the particle, the circuit with the detector, the computer with the circuit, creating an ever-expanding web of quantum correlations without any natural breaking point where collapse occurs. Yet we never experience superposition directly. We don't see detectors registering contradictory results or computers displaying multiple outputs simultaneously. Somewhere in this measurement chain, quantum possibilities transform into classical certainties, but the theory remains mysteriously silent about where and why this transformation happened. This silence has forced physicists to propose various interpretations, each attempting to resolve the paradox through different strategies. The Copenhagen interpretation suggests that quantum systems simply don't possess definite properties until measured, making measurement the creative act that brings reality into being. But it deliberately avoids defining what constitutes measurement, leaving a conceptual void at its core. The many worlds interpretation eliminates collapse entirely by proposing that all possible outcomes occur simultaneously in parallel universes. Measurement becomes the branching point where observers split along with reality itself, each experiencing one outcome while remaining forever isolated from alternative versions. This preserves mathematical consistency but requires accepting an infinite multiverse of parallel realities objective. Collapse theories propose that wave functions collapse spontaneously when quantum systems reach certain thresholds of size or complexity, making collapse a natural physical process rather than something triggered by observation. These models make testable predictions, but introduce new physics that hasn't been experimentally confirmed. Decoherence theory focuses on how quantum systems lose their coherence through environmental interactions, explaining why macroscopic objects behave classically. The environment acts as a continuous measuring device, entangling quantum systems with countless surrounding particles. This explains the disappearance of quantum interference, but doesn't fully resolve why we experience one specific outcome rather than a statistical mixture of possibilities. Some interpretations suggest consciousness itself plays a fundamental role in collapsing quantum systems, Perhaps the universe remains in superposition until observed by conscious minds, making awareness a physical force that shapes reality. While philosophically intriguing, this approach often draws criticism for being difficult to test and potentially unscientific. More recent approaches explore information-theoretic foundations, suggesting that reality emerges through the formation and preservation of records. Quantum Darwinism proposes that certain information becomes redundantly encoded throughout the environment, creating the appearance of objective facts that multiple observers can access independently. Reality might be what becomes sufficiently recorded and cross-referenced to survive scrutiny. Each interpretation solves certain aspects of the measurement problem while creating new puzzles. They represent different ways of trading one set of conceptual difficulties for another, highlighting how deeply the measurement mystery challenges our fundamental assumptions about existence. Perhaps the measurement problem persists not because we lack sufficient mathematical tools or experimental data, but because it points toward aspects of reality that transcend our current conceptual frameworks. It suggests that understanding quantum mechanics fully might require not just better physics, but entirely new ways of thinking about the relationship between observation and existence, between consciousness and matter, between mathematical description and lived experience. The measurement problem transforms our understanding of science itself. We're not passive observers studying an objective reality that exists independently of our presence. Instead, we might be active participants in an ongoing process of reality creation, conscious beings whose observations help determine which version of the universe crystallizes from quantum possibilities into concrete experience. This realization brings us to a crucial recognition. Every paradox we've encountered isn't just revealing gaps in scientific knowledge, they're pointing toward a fundamental transformation in how we understand our place in the cosmos. The universe revealed by quantum mechanics operates according to principles far stranger and more participatory than classical physics suggested, where the boundary between observer and observed, between mind and matter, between possibility and actuality, becomes far more fluid and mysterious than we ever dared imagine. Standing at this threshold between the known and unknown, between mathematical formalism and existential mystery, we find ourselves confronting not just the limits of current physics, but the deeper question of what it means to exist as conscious observers in a quantum universe that seems to require our participation to become fully real. The profound realization that we might be active participants in reality creation rather than passive observers brings us to the culmination of our quantum journey, where every paradox we've encountered converges into a single, transformative recognition. Standing at this threshold between the known and unknowable, we find ourselves not at the end of a mystery, but at the beginning of a far deeper understanding of what it means to exist as conscious beings in a universe that seems to require our participation to become fully real. Each paradox has served as more than a scientific puzzle. They've functioned as cracks in the foundation of classical reality, revealing glimpses of something far stranger and more wonderful beneath. The double-slit experiment showed us that questions carve reality into the shapes we later discover. The delayed choice quantum eraser demonstrated that these carvings can be constrained by future decisions, suggesting time itself might be more like a completed puzzle that consciousness traverses piece by piece rather than a flowing river carrying us from past to future. Wigner's friend revealed that the very notion of objective reality might fragment along the lines of observation, with different observers experiencing genuinely contradictory yet equally valid versions of the same events. Retrocausality hinted that initial and final conditions might conspire together to select histories, making the universe less like a mechanical sequence and more like a constraint. Satisfaction problem solved across all of space-time simultaneously. The silent coordination of quantum pseudo-telepathy exposed connections that transcend our classical notions of separation. suggesting that what we call distance might be merely a bookkeeping convenience for macroscopic creatures, while the universe maintains its own deeper accounting system through entanglement. The quantum Cheshire cat revealed that even the bond between objects and their properties can dissolve under careful scrutiny, showing us that particles might be less like tiny nuggets carrying traits, and more like webs of dispositions that different measurements can tease apart. The quantum suicide thought experiment pushed these insights to their most personal extreme, forcing us to confront what it means for consciousness to persist through a branching multiverse where experience might always find survivable paths. And the black hole information paradox bound all these threads together with an unforgiving demand that information be preserved, even when it seems to vanish beyond cosmic event horizons, suggesting that the universe will rewrite our intuitions about space, time, and existence itself rather than allow fundamental principles to be violated. Together, these paradoxes reveal a pattern that transforms our understanding of science itself. We are not separate entities studying an external world from a privileged position outside the system. Instead, we are embedded within the fabric of reality as conscious patterns whose observations and choices participate in the ongoing process of determining which possibilities crystallize into definite experience. The questions we choose to ask don't simply reveal pre-existing answers, they help determine which answers become possible. This recognition doesn't diminish the human role in cosmic understanding, but elevates it profoundly. We are not passive receivers copying text from nature's stone tablet, but careful co-authors working under constraint. The equations and experiments veto our laziness and wishful thinking, but they also invite us to participate in reality's creation through the choices we make about what to observe and how to observe it. The implications cascade through everything we thought we knew about existence. Consciousness might not be an emergent byproduct of complex matter, but rather an integral aspect of the universe's capacity for self-observation. The hard problem of consciousness, how subjective experience emerges from objective physical processes, might be asking the wrong question entirely. Perhaps consciousness and matter emerge together from some more fundamental level of reality that transcends both, making awareness not something that happens in the universe, but something the universe does practically. This strange world already pays dividends. Quantum computers leverage superposition to explore many computational paths simultaneously before measurement selects an answer. Quantum sensors dance at the edge where information first becomes available, pushing past classical limits through careful manipulation of measurement contexts. Quantum communication schemes turn entanglement into unbreakable security guarantees. The paradoxes that trouble philosophy are the same features that power technology, reminding us that usefulness and mystery are partners, not opponents. Yet humility remains essential as we stand at this edge. We may be approaching not just the limits of current knowledge, but the boundaries of the metaphors that carried us here. Newton's gears, Einstein's fabric, Schrödinger's waves, each served as a conceptual ladder to wider understanding, and each must eventually be transcended. The next framework may not resemble anything we currently recognize as physics, but rather a fusion that integrates mathematical description with conscious experience, objective measurement with subjective awareness. The path forward involves building experiments that force nature's hand in the gray zones between quantum and classical behavior. We cool mechanical objects toward their quantum ground states, interfere ever larger molecules to watch coherence dissolve, perform Bell tests across cosmic distances, create laboratory analogues of black hole horizons, and test objective collapse theories against our most sensitive instruments. Each probe sharpens the map of reality's true boundaries. With each experiment, the universe continues its patient instruction. It doesn't grant us the comfortable illusion of complete understanding, but it has been unfailingly consistent in its lessons. Reality is relational rather than absolute. Information is physical rather than abstract. Context determines what becomes real rather than merely revealing what was already there. The future participates in writing the past through quantum correlations, that respect causality while transcending our naive understanding of temporal sequence. These aren't failures of current theory, but invitations to expand our conceptual vocabulary. The universe revealed by quantum mechanics operates according to principles of complementarity, non-locality, observer dependence, and participatory reality that point towards something far more subtle and interconnected than classical physics suggested. Standing here at the edge between the mapped and unmapped territories of knowledge, we find ourselves in a position remarkably similar to the early quantum pioneers. Like them, we face phenomena that challenge our deepest assumptions. Like them, we must choose between clinging to familiar concepts that no longer adequately describe what we observe, or venturing into conceptual territories that feel alien and unsettling. The paradoxes continue whispering their patient instruction, pointing toward a universe where consciousness and cosmos dance together in ways we're only beginning to glimpse. They tell us that we're not just studying reality, we're participating in its creation through the very act of conscious observation. The universe isn't simply happening to us. In some profound sense, it's happening through us, with us, as us. The whispering scientist listens still, for the universe always has more to say. Each paradox opens doors we didn't know existed until we reached for them. Each mystery reveals new depths of wonder, and each answer births better questions that guide us deeper into the heart of what it means to be conscious beings, helping to create the very reality we inhabit.